Hi students, let us continue with the signed integers. In the previous video, I explained about the sign and magnitude. That is one of the representation of signed integers. Now let us see the next type of representation of signed integer, that is ones complement. So here in the ones complement, the negative numbers are complemented to positive and the positive numbers are complemented to negative. But you no need to complement if the result is positive. So the only thing, if the result is positive, means not result, the question, the problem is whatever a decimal number is a positive, so you no need to convert into ones complement. Only the negative numbers are complement of positive numbers. So and ones complement, the main use is it is less costly to implement it. So the main the ones complement means ones complement means just reversing the all bits. You have to just reverse. If 0 is there, you have to make it as 1. 1 is there, if you have to make it as 0. Just reverse whatever the bits are there. Ones complement is reversing all bits. Positive numbers becomes negative, negative numbers becomes positive. So if you make ones complement a number of if you take any ones complement, you can make that number as twice ones complement, you will get the original number. Okay, so once you make that number as ones complement, again you make it as ones complement, you will get the original number. So now let us see the examples for this. So before going for examples, I'll just show you that how the ones complement is represented. So this is a signed integer ones complement. So here storing ones complement in two different computers. So that is 8-bit location and 16-bit location. So the decimal numbers for signed integer, so plus 7, minus 7, plus 124, minus 1, means whatever the number you want you can take. So here I have taken only numbers randomly. Plus 7, minus 7, plus 124, minus 124, plus 24760, minus 24760. So the 8-bit memory location, if you want to convert this decimal number 7, you have to represent like this. Here it is plus. So the most significant bit here, this is 0. Minus. So you have to make this as just complement. Just complement means just reverse the bits, because this is negative. Whenever the negative is there, make that positive number reverse and you will get that negative value. So instead of zeros, I'm just placing here it is a ones, and in place of ones I'm putting it as zeros. So this is the negative minus 7 value that stores in 8-bit location. So this is a value of plus 124. So if it is minus 124, just you have to reverse the positive number. So here just reversing the positive number. So in place of 1, 0, 0 place 1. So here minus plus 24760, this is overflow. Always the range is between from up to 254. Okay. And this is for 16-bit allocation. So the same for 8-bit, but instead of 8-bit you have to make it as adding zeros, so you will get the 16-bit allocation. So minus 7 means you just make it as a complement. Reverse the numbers. So whatever the 0, in place of zeros, just place ones. In the same way for 124. Okay. So just complement. Reversing the numbers. So this is about the ones complement. Let me explain with some examples. I'll take some examples here. Example 1. The same procedure, store plus 7 in 8-bit memory location. I want to store plus 7 in 8-bit memory location using ones complement, not sign magnitude, using ones complement representation. Okay, so write the solution. So the first step you have to follow what I said, change the number to binary. Change to binary. So whatever the decimal number they are given, first you change to binary, because the system can understand only the binary numbers. Change to binary. 1 1 1. So now I'm add 5 zeros. So why in the sign magnitude I add only 4 zeros? Because the last leftmost significant bit represents the sign magnitude. If the number is positive, the last bit, that is the most significant, leftmost significant bit is 0. If it is minus, the leftmost significant is 1. So that's why I add only 4 zeros. After that I will add 1 or 0 to the last bit. But here I am adding 5 zeros to make total of 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So total I get 8 bits. Now I am checking. The sign is positive. Here it is positive. So no more actions are needed. So whenever it is positive, no need to complement it. Whenever it is a negative, then you have to complement. So the sign is positive. So whatever they are given, that is a positive sign. So no more action is needed. So then the result is just 5 zeros, 1. Total 8-bit memory, 8-bit size, and it stores in 8-bit memory location. Now let me take the negative number this time. For 1's complement, store minus 258 in a 16-bit memory location using 1's complement. Using 1's complement representation. So first step is you have to change that to binary number. Change the number to binary. So 255 representation is 1. So this is the 255 representation decimal to binary. Now add 7 zeros. Instead of 6 zeros, I am adding 7 zeros because I am just representing it into 16 bits. 7 zeros to make a total of n 16 bits. So add 7 zeros. 1, 2, 3, 4, 5, 6, 7. 1, 1, 2, 3, 4, 5, 6. So this is completely 16 bit. Here they are given the sign as negative. Now what I have to do? The sign is negative. So each bit is complement. You have to make each bit is complement. Complementing means just reversing whatever you get that. So the result is, so what is the result here? So just complement it. 7 0 1 1 5 6 7 0 1 1 1 1 1 1 0 1. Just I reversed whatever the number we get, that I complemented because it is a negative number. So this will stores in 16-bit memory location. So this is how you have to represent a 1's complement using positive and negative numbers. Thank you.